Good afternoon and welcome to today's webinar titled Selecting Parts for Additive Manufacturing, presented by SLM Solutions and hosted by 3D Metal Printing Magazine. My name is Brad Kuban. I'm the publisher and editorial director of 3D Metal Printing, and I'm pleased to serve as your moderator today. Before we get started with the webinar, just a few notes about today's GoToMeeting session. The meeting is being recorded for archiving, and the recorded event will be posted to our website within the next few days. Once we do post it, we'll send you an email to show you where the recorded webinar is available for viewing online, watching again, sharing with others at your company. Also, I want to let you know that all of the participants in the meeting are in listen-only mode. That means that the speaker and other listeners will not be able to hear any audio from your site during the program. However, you do have the ability to communicate with us throughout the program by submitting your questions and comments using the question box, which is located on the right-hand control panel on your GoToMeeting screen. Simply type your question to an organizer as selected from the drop-down menu. You also use that same question panel to ask questions from our speaker at the end of the presentation. So let's go ahead and get started with the webinar. As metal additive manufacturing continues to expand as a viable production process, many companies are assessing the viability of producing parts with selective laser melting. The objective then of today's webinar is to offer tips for helping you understand what types of parts, features, and geometries are best suited to be optimized for additive manufacturing, and then also help you understand what might make the process unfeasible as well. You'll gain an overview of how to assess your components to take the first steps in implementing a metal additive manufacturing strategy. Our speaker this afternoon is SLM Solutions Applications Engineer Kyle Adams. Kyle is a lifelong car enthusiast and has applied his automotive background throughout his career, spending 4 years in reverse engineering of transmissions and driveline components before he joined SLM. Kyle is currently responsible for operating SLM's Technology Center, where they push the limits of what is capable with the 5 metal powder bed fusion machines in the lab, while consulting with customers on feasibility and optimization of their own selective laser melting projects. So without further ado, please welcome Kyle Adams.
Thank you very much, Brad. Again, I'm Kyle Adams, and we're going to be talking about selecting parts for additive manufacturing. And let's get into it. So I'm going to start with a quick introduction of SLM Solutions as a company. SLM Solutions is based out of Lübeck, Germany. It's in the north, just south of Denmark. This is our new manufacturing and engineering facility that's seen pictured here. As well as Germany, there are 5 other offices throughout the world, United States being the one that handles the North, Central, and South America. For that North America office, founded in 2012. We have over 30 sales, marketing, customer support that includes application and field service engineers. And at this point, we have well over 150 installs. Out of this particular lab in the Detroit metro area, we have our 5 powder bed systems, including a range from our smallest system up to the SLM 500, which is our second largest system available. From there, we do demo parts, we do pre-customer support and post-customer support, building parts for those particular customers for viability and feasibility. As far as the machines available, these are the 4 main current systems available, the SLM 125, 280, 500, and 800. All those numbers really according to some measurement of the plate size. The SLM 280 is the main system that we sell the most. It is a very, very flexible system, being able to reduce the build chamber down, but also be good for doing full serial production in. And a lot of what we worked with today and a lot of what we're going to talk about has been done on the SLM 280. So SLM Solutions, we've really in the past handful of years been very active in the aerospace and energy markets. And fairly recently, automotive and healthcare have really started to come around due to the increased productivity available, which ends up driving down the part cost significantly. So these are the areas, as well as tooling. So being able to make very quick tooling, very strong tooling, as well. These are the areas that metal additive and powder bed metal fusion seems to operate and work the best in. Some of the advantages of the SLM technology, obviously, are freedom of geometry, the reduction of build time in comparison to getting a casting done, the reduced part cost by decreasing material and decreasing those build times, our increased part properties compared to, say, a casting, and then being able to use bionic geometries, prototyping, dental and orthopedic implants. We can custom make those perfectly fit for the particular customer. And then as far as indirect, the speed and flexibility of the systems, being able to print something one day and print a completely separate geometry at the very next job without having to retool or reprocess. The weight savings from the part themselves are really handy for things like aircraft and also automotive for trying to reach fuel economy numbers. Part integration is a great value because we're able to take multiple pieces, sub-assemblies, turn them into a single assembly, and be able to create one part number there. That decreases your supply chain and increases the economic value of having the metal additive being able to produce one particular part. And then the eco-balance. What we're printing is the material that we're using, so there's not a lot of wasted material between every job. We're going to cover some more of these points while we go through the process and while we go through this presentation. So this title is actually something that my previous boss and mentor told me. 3D printing is easy, additive manufacturing is hard. So let's extrapolate on that. These are all the steps that you need to do to consider something additive manufacturing. And I like to say, in this industry, people like to avoid the term 3D printing. It seems like it doesn't properly cover what we're doing. Well, 3D printing is, some people do 3D printing. 3D printing is taking any single file available and making it work for the system, making it work for the process. Where additive manufacturing is taking a part, having a design concept, and working with that part through the entire process to make that part fit the process and make the process fit the part, to have that synergy of having an additively manufactured part that is easy and makes the most sense on an additively manufactured system versus 3D printing of taking a traditional part and being able to build it with a 3D printer. So these are a handful of the steps that you go through in just creating a part: the design, the production plan, approvals, job prep, running, setting up the jobs, actually printing the part, the powder removal, stress relieving, heat treat, all the way down. All these steps are very time consuming. Each one of them for a qualified part takes a long period of time, and sometimes it can take up to a year or even more to get a single part qualified for production, say for FAA approval. And so this is a lot of very hard work. It takes many people and hundreds upon hundreds of man hours and machine time and cost to create something for the quote unquote additive manufacturing. And a little bit more about that process. So we start with a model. Typically we use an STL model, a wrapped triangular model. That model is then supported. So an additively manufactured part, which has design considerations for build orientation, might not need support, but a more traditional part may need support material added to it. That material is the same material as what's being built inside the system. It is not a secondary or a dissolvable material. From there, we add our slicing. So this is where we're going to break our part up. As we build this, we build these in typically 30 to 60 micron layer thicknesses. So we have to take that entire part and break it down into our individual 30 to 60 micron layers, depending on how we want to do that. From there, each layer is then sent a hatching pattern. That is our actual machine pathways, our laser speed, power, and focus, and how we're handling the laser to actually print our part. There's a lot of intellectual property and there's a lot of research that goes into the proper hatching patterns, because that's how we're getting our mechanical properties and how we're controlling the mechanical properties of the material itself. From there, it is exported into what we call a .slm file. This is your fully finished file, which then can be exported and sent to the machine. From there, the machine reads the file and starts printing the part. So we add our plate, we add our material, the file is then loaded, and the printing process is then started. So here's a quick video of currently an SLM 500 with 4 700 watt lasers being able to build parts. And you can see that you have multiple lasers working on the same part. So the typical machine, metal additive, you're working at 75 micron spot size and an average of 30 micron layer thickness. Now the layer thickness is dependent on what you're looking for. So there's 30, 60, and then for reactive materials, 90 micron layer thickness. For the 30 and 60, these are high quality, 30 is a high quality, high resolution, slower build speed. 60 is a good balance between high resolution and high speed while good quality. And then the 90 micron is a very high pure casting replacement where we're going to have very high throughput, 3 times faster than our 30 microns, good quality, but your resolution may have dropped a little bit just because we're building 3 layers for the same that would take, one layer for the same that would usually take 3 layers. And as you can see with this video, we're doing bidirectional recoding. So every time that recoder moves, about 8 seconds, the machine is laying down a new layer and building a new part, or building a new layer of the part. So there's 7 things we're going to talk about today when we're considering a good part for additive manufacturing. And these are 7 questions that I suggest that you start looking over and, maybe make some edits to them yourself to make them fit you. But these are the 7 questions that we ask ourselves when evaluating a potential customer part to see, does this part make sense for us? That first one, does it fit? Does the part fit within the plate? So a 280, which you see here, is the plate is actually 278 millimeters square. The Z height in the 280 is 365, but then we subtract the height of the build plate itself. So it's a 25 mil plate, we subtract that 25 millimeters. As you can see, there's area for bolt holes there, clearance, which ends up being about 15 to 20 square inches of material placed area removed. So is the part we're looking for, is it a big, huge part that just say metal additive, powder bed additive manufacturing doesn't have a machine for? Are these smaller components where you can fit multiple within the plate, or say one large component that fits within one part per plate? So does this part fit, and can we get it to work with a particular system that's available? It's an easy one, but it is a good first step. Material, does it weld? Metal additive is a glorified welding process. We're using a fiber laser to weld this material, and when we're done, we have miles upon miles upon miles of weld beads stacked upon top of each other. So does the material weld? These are what we're looking at as kind of a standard list of materials that SLM provides. Our aluminum, our cobalt chromes, Inconel, titanium, and tool and stainless steel. The ones that are highlighted are more of the standard, very commonly used materials that are being currently being used. That being said, additive was initially designed as a process around pre-established materials. So these are pretty established materials. Additive is reaching a point now where the material development is outpacing the machine development. So materials such as copper and new 6061 aluminums, other nickel-based space alloys, and titaniums are being introduced into the market and testing and working with this new additive process. So every day, there's new materials that are being added to the system and being added to your capabilities. SLM is an open system, so we do provide these materials and parameters, but that doesn't prevent you from running a separate material or parameter set that is completely open to you. And one of the benefits of powder bed fusion is that the cost of material is significantly, or pretty insignificant, to the total cost of the process. So saying if your typically manufactured part is in 316 and you wanted to print it, maybe the cost of material to move up to, say, Inconel 718 is going to be pretty small compared to the overall process cost. So being able to increase your performance by increasing or changing your material to a higher performance material is entirely possible. And it's something that we look at quite often as a selling point of additive manufacturing, where it may be cost prohibitive to do Inconel 718 in a traditional cast or traditionally 5-axis subtracted machine part. From there, the economics. So we're starting to talk about cost a lot. Is there value in the parts that we're making? Here is a cost estimation form. So just like all other manufacturing processes, we understand what goes into the machine very, very well. How much gas we need to use, how much electricity, power, all of these values that go into how much your end part ends up costing. And this is a large part of what we do in the Wixom office, is taking parts from potential clients and saying, this part will cost you X amount. How does that make sense in comparison to the way you're currently making it? And so does this new additively manufactured part make sense in, say, supply chain reduction and part cost reduction and assembly, cost reduction, to build it additively versus building it traditionally? And sometimes there's very simple parts that can be either, say, stamped or die cast or MIM or anything like that, where it might not make sense to build additively. And there are a lot of parts that still don't make sense to build additively. So it's a very fine line of understanding what parts do make sense. And the general rule of thumb is with the increased complexity comes an increase in value of that particular part. And for that, the economics, we say that each machine can produce about 1 ton of material a year. So design dependent, completely independent of design, you can put about 1 ton of material through a system each year. So if you have 5,000 kilos of material, you can say, okay, 5,000 kilos, we need about 5 systems to be able to produce 5,000 kilos of material every year. So we kind of look at those numbers and what those numbers end up meaning for that particular design. Do we need 1,000, do we need 1,000 kilos? Do we need 2,000 kilos? And then deciphering how many machines make sense to run that process. And here we're showing that it's not always large parts. It's sometimes small parts with high complexity. This particular example is what's called a stealth key. This is a highly secure key that's used for a lot of government facilities. And as you can see on the right-hand side, the key geometry is actually hidden behind these shrouds. So the only way you can make this is by 3D printing this key. This key then cannot be copied, it can't be duplicated, but it is still a physical key. And on a SLM500, we were able to build over 1,100 of these parts every single run. So that ends up making a lot of sense when you can pack the plate completely edge to edge. You can see there that that plate is completely packed front to back and edge to edge, excluding areas for the bolt hole clearances, which we talked about earlier. So every single run, building 1,100 makes a lot of sense. This wouldn't make sense if we could only build 400 or 500 parts per plate. It makes sense when we can actually pack the plate down and fit as many as possible. And just here's some examples of high value, high performance material. So what we're getting at is there's got to be high value in these parts. Transmission housings, cylinder heads, the brake calipers, and some of these examples we'll go for later. But is there a high value for the part you're building? If it's a low value stamped piece or a low value MIM piece, then it's going to be very hard for Metal Additive to make the justification for that particular part in production. But if it's a high value, high complexity piece that requires a lot of post-processing or a lot of part integration, then these parts start to make sense. Performance. So it fits, we have the material, the numbers start to make sense. Our next area, the next question is our performance values met? Can we make material that meets your specification? So powder bed metal is its own class and category of metal. You can relate it to something, say wrought material, within 1% to 2% of wrought material, but in the end of the day, it is its own material with its own microstructures and its own porosities and its own issues. So what we see here is actually aluminum alloy as printed, and you can see the laser pathways and the overlaps and all of the layers on top of each other and the microstructure and the melt pools. And you can also see there's a small piece of porosity. So this is, when going through qualification and understanding this is the type of material that we're going to get out of the system. And we can't just replace whatever you're using with just a standard material. We need to understand the mechanical properties required out of that, out of your requirements, to understand what material works best for your application. So here's some pretty important mechanical properties, kind of the 6 main ones that everybody looks at. And as you look at them, 2 to 4% within wrought material. So surface roughness. it's not going to be a machined surface, and surface roughness is very dependent on our layer thicknesses, which we talked about earlier. 30 microns is going to be a lot smoother than, say, 90 microns. That's just a function of more layers, finer steps. Our material strength, we do a lot of testing material strength for X, Y, and Z, because metal additive is not like subtractive, where you can take an ingot and understand the exact mechanical values of that ingot, and then whatever shape you make it into will have the same mechanical values. As we're printing, the mechanical values can change in X, Y, Z, and then based on heat input, there's so much more that goes into metal additive that we really need to understand these values pretty deeply. Part accuracy. So it is a near net shape, 50 to 100 micron accuracy across the course of an 11-inch plate. So over the course of 280 millimeters, holding 50 to 100 microns, you're not going to be printing threads and having them be perfectly located, but you'll definitely be able to print guidance holes and post-machine perfect location threads very, very, very accurately. And then stress. Since this is a welding process, welding tends to build up a lot of heat and a lot of stress. So what we need to look out for is that the stress within the part, and how are we keeping that stress, and how are we going to relieve that stress. Because believe it or not, you can take a solid piece of metal, not stress relieve it, cut it off of a build plate, and that entire part will just warp. Big, thick chunk of metal will just warp because of all the stress that's inside of it. So stress relief cycles and heat treat cycles to make sure that our parts are going to stay the same shape once we cut them off the plate. And 99.8% density and above. So 99.8, 99.9, these are the densities that we achieve and we strive to achieve. And if we're looking at lower than that, we've actually reached a point where we're starting to look for issues. That being said, because we can control the process so well, there are applications where you can increase your porosity to achieve different mechanical properties, even to the point of creating porous filters out of metal powder bed additive. And then hardness. So again, within 2 to 4% of raw material, but how are we achieving our hardness, and how have our heat treat values affected our hardness of our material? Qualification. This is another very simple step, but it's also a very complex step. Is it yours? Do you own the design, and do you have the rights to make this design out of powder bed? So if somebody comes up to you within a company and says, I need this part made, and you decide to go to powder bed, do you have the right to do that? Do you own the rights to make it out of powder bed fusion versus a traditional manufactured part? Is that what is available? So a lot of engineering designs call for, what specifically you can use to make this part. So, and if you can go to additive, what type of requalification processes are needed? What kind of costs are incurred by going to an additively manufactured process versus a traditionally manufactured process? Design. So this is where we're going to get into some of the design elements and design iterations of what we're looking for when we're looking at parts in particular, in our first, gut instincts on what a part would work and what part won't work. So we're looking at design here. We're actually looking at the bike suspension piece that is traditionally manufactured, and though it would work in a system, it's going to move, and we're going to go from a casting to a machining for optimization down to an additive optimization. And you can see that there's at least 4 different iterations there and completely separate looks. And so with additive, it's a much more organic shape. So a lot easier to make. It would be very hard to make on a 5-axis system. There'd be a lot of movement there. There'd be a lot of programming. But with additive, it's a quite easy piece to make. And what you can see here, actually, there was a lot of support material there. So though it may be organic in shape, it may not make sense. You can see there's overhangs. There's areas where the typical rule, and this is just a very guidance rule, is 45-degree overhangs for metal additive before you need support. So anything over 45 degrees will then need support material added, and that support material will then need to later be removed. So there are design softwares that will allow for build orientation and design the part properly based on that orientation to reduce, or if not completely eliminate, the amount of support needed to build that part. Post-processing, is it painful? And we'll still touch on some of this because we're going through some examples. We'll still touch on some design elements here. So what needs to be done during post-processing? quality verification. So CT scanning, dimensional analysis, is this part dimensionally accurate? Stress relief, hipping, heat treatment, removing from the plate, support removal, and surface finishing. These are about all the steps that you need from the part leaving your machine to having a fully finished part. We can see here on the right-hand side, there's two pieces. There's what looks like a very organic bracket. Though it's very organic, there's a lot of support material within that part. You can see it on the picture on the left and the middle picture on the right. There's a lot of support material that needs to be removed. Now, that may not be the best orientation. That part can be changed. The picture above and below that, that part is 100% support free. It is welded to the plate. It's support free all the way up. That is a very easy organic part to print. For quality verification. So CT scanning allows us to do non-destructive testing. It allows us to look within a part. It allows us to see any porosities within the piece to a very, very finite level and understand our parameters are making the material that we're looking at. So without that, without CT scanning, you need to do destructive testing. So cutting the part open, looking at porosities, looking to see, okay, in this particular section, we have porosity. That means we need to extrapolate the rest of the part will have porosity as well. And then also CMM inspection. So scaling the material. As the material heats and shrinks and cools, you know, these parts tend to move, and we can scale the material to get within that 50 micron accuracy, but we need to create those scaling values in the first place to understand how our material is going to move while we're building with it. After that, stress relief. So we see two different types of stress relief furnaces here. Again, this is a welding process. Even parts as low stress as aluminum tend to warp as we cut them off the plate. So materials that, you know, if you're just doing a simple stress relief, a furnace on the left-hand side with an argon blanket may do just fine. But if you're going to do stress relief and even heat treat, including things like titanium, which has a high potential of picking up oxygen, a vacuum furnace like we see on the right may be an investment that's needed, or at least find a provider for vacuum furnace heat treating to be able to heat treat these parts and one, achieve mechanical properties, but also two, relieve stress and prevent warpage of the parts coming off of the plate. Another option is what's called hot isostatic pressing or hipping. Hot isostatic pressing is very interesting because what it does is it heats up the entire part uniformly and applies a high, very, very high amount of pressure to the part uniformly through air. And what it will then do is heat the part up enough that we're able to close up any internal porosities. So this graphic we see on the right, we can see that this is the same part, same microstructure, same area, and just due to the high pressure and the heat, we're able to close up all those porosities and seal up the part to a fully dense piece. This is actually going through and changing the microstructure of the part itself and changing the way the mechanical properties are affected by this part in HIP. The thing about HIP is a very expensive process, and it's a very expensive machine. It's very time consuming. So hipping is usually done on aerospace components where it's absolutely necessary and required to meet certain densities. And it's not always the best solution for all parts because of the increased cost per part incurred. Next is removal from plate. What we see here is three separate ways that we go about removing the parts from plate. One, wire EDM. This creates a very, very clean cut, very, very almost finished surface cut. One thing is it's very slow and it's a very expensive system. The next one, bandsaw. Bandsaws are very quick compared to wire EDM. They're significantly cheaper compared to wire EDM. You don't have things such as wire and solution. It's just a saw blade and we're cutting parts. This is metal, so blades, you know, metal blade, cut through metal parts. It still may take 20 plus minutes to cut through a big, thick section apart, but it's an overall very cheap process. This is actually SLM Solutions bandsaw that we have in our office that we use to cut our parts off. And then the last one, which we saw a quick video of and we'll show again here, breaking right off. So this is when thinking of additive manufacturing, 3D printing dream, you print a part, you take it off out of the machine and you break it right off the plate and it's done. The, you know, quote unquote Star Trek 3D printer of the future. You put it in, bang, parts printed, rip it off, no post-processing needed, the part's done. Not all applications fall into that. In fact, very few applications fall into that, but that is the goal that, we strive to achieve, is this, perfect part that just breaks off and we're moving on. And we don't need to do any post-processing, no bandsawing, no EDM. It's a very simple process, and we're done. Here's a video. So people always ask, how hard is it to remove support? We actually have videos. So this is a part, a smaller version of the bracket we looked at earlier. You can see the support material on there, and we're breaking this off by hand. So there's a handful of options, one of them being 5-axis machining, but by and large, supports are removed by hand with tools, with hand tools. So we're seeing, this is actually Rick, our shop operator, cleaning this part off, removing that support material, and you leave left with a somewhat rough surface where the support material attached to the part. And that's why it's very important, one, to orient the parts properly, but two, support the parts properly, because sometimes supports can be left within areas, say internal volume passages or internal cooling passages, where the support can't be reached and the support can't be removed. So we need to make sure that we design the part in such a way and design the support in such a way that we're not leaving support in places that we can't reach it. And this is the same material. So once this material is printed, it has to be scrapped. It can't be reground and added back into the powder bed process. So another thing is reducing the part cost is reducing the amount of support needed, because at the end of the day, that support is just wasted material. We can't use it. So we need to make sure that we limit it to a point where it makes sense that we're supporting this properly, but also keeping the part supported so that it finishes its print. And then surface finishing. This is fully dense metal when we're done. So you're grinding it, sanding it, electropolishing, bead blasting. They all work just as well as any traditional material. So one of the systems that we like to use and we like to see a lot is this electropolishing system, because in a very short order of time, you can reduce the overall surface roughness in a very uniform fashion on additively printed parts. And you can see here this part printed from as printed to grit blasted, and I believe this was 20 minutes within, not grit blasted, electropolish. 20 minutes electropolishing, and this part is complete. And you have a near mirror finish on the part. While we're looking at this part, a few of the things that we'll notice is that those holes aren't round. So for design, that hole was designed in a teardrop fashion. The reason that's done is that hole can now be printed support free, because as that hole closes up, there's no support needed because we never reach an over 45-degree overhang. So that's a design element that was designed specifically for the additive process. Examples. So one of the success stories, the convertible top for the BMW i8 Roadster. You can see here that, from initial design iteration all the way through down to the fully finished part, the reduce in mass and size, but also the increase in organic shape, and that's the part we saw break off the plate, the reduced complexity of post-processing this part. So not only is it a lot easier to manufacture this part and lighter, but also 10 times stiffer than the plastic injection molded piece. So they're using aluminum to produce this part. Aluminum is going to be much stronger than the plastic injection molded piece. So not only is it stronger, but it's lighter as well. So there's dual benefit there. And going through this, as we're figuring out, we've gone through these 7 questions, let's ask ourselves, size. Does the part fit? Yes, they can fit over 500 on a plate. Does it well? It's aluminum ALSI 10 mg, so the material makes sense. Is there value in the economics? It's a very expensive sports car, but also they're able to produce a lot per build, so the value is there. The performance isn't met. Well, the performance is actually exceeded compared to the traditionally manufactured parts, so we're going to give that a check. Our qualifications, BMW designed, BMW built, designed for the metal additive process, check. Will it work? This part is in production. If you were to go to a dealership today and look at this part, it would be sitting there on the showroom floor. And then post-processing. This is, again, the prime example of this post-processing is not painful. This part was designed in such a way, and the work was done so that the post-processing is minimal at best. So post-processing, it was not painful. Very easy part, very good great example of metal additive manufacturing in current production. This next part we're going to show here, we've touched on a little bit, and this is also a part that's been talked about quite a bit in the space of additive manufacturing, the Bugatti brake caliper. So that part is built on a SLM 500 out of titanium. The traditional manufactured part is aluminum, and it's a forged component. So this part is now 3D printed out of titanium. Part was removed, powder's removed, it goes into wire EDM to cut the part off of the plate. Through the magic of movie editing and post-processing, the part is then completed, polished, and finished. So here is the completed part to be added to the $2.5 million sports car. Let's look at some of the numbers of this part. So tensile strength, it meets or exceeds that of the forged component there. The dimensions, very big part, but again, fits on a machine. And it's 2 kilos lighter than the machine's aluminum counterpart. So in automotive, unsprung weight is king. Reducing unsprung weight is some of the most important for performance, for economics, and value of the machine. So brake caliper's unsprung weight it's weight that's not held up by the spring in the vehicle and the suspension of the vehicle. So reducing 2 kilograms per corner is a massive amount of weight loss. Build time, 45 hours. It's a long build, but this is a very, very low production number, very high performance piece. And the functional testing. So again, this part was function tested to perform better than the traditionally manufactured aluminum piece. So again, looking at this, does it fit? Yep, we were able to print 1 per job, but it still fits within the SLM 500. Does it weld? So again, we talked about swapping materials to get an increase in performance. So we went from an aluminum, traditionally manufactured aluminum piece, to an additively manufactured titanium piece. So going from aluminum to titanium is probably one of the biggest swings in material for metal additive, but the price is so insignificant compared to the overall process cost that it was worth it for the increase in performance and the decrease in weight. Is there value economics? Well, it's questionable because not everybody can afford $2.5 million for a sports car, super sports car, but for Bugatti, for VW Group, this part does make sense. Is it met? The performance is actually exceeded not only in weight, but also in the actual braking performance testing. Qualification, Bugatti owned, Bugatti designed, testing on a brake bench to make sure that this works from its lofty speed of over 300 miles an hour. With the restrictor off, this part works. And design, will it work? They've proven it, design works. And post-processing, again, this part required a lot of post-processing, EDM, hand removal, and polishing and machining. But compared to a forged piece, this part still makes sense for post-processing. Another piece that is a good example of talking about integrating parts and actually increased performance is this motor bracket, which would have a bearing inside the circular housing there. And what we see on the top right corner is that there's actual water cooling traveling through this bracket. So there's internal water cooling in this bracket that keeps that bearing cool during high performance runs and during high performance operation, which prolongs and extends the life of that bearing. And I'll get to a huge performance increase because that bearing doesn't need to be replaced. And that is on production on the vehicle right now. How about spacecraft applications? So here is a fuel valve body that is printed out of titanium. This part was traditionally cast. This part would crack a lot during casting. So being able to go to metal additive manufacturing, we're able to control the inputs significantly better than casting, and we're able to prevent the cracking on this part almost completely. Now, this part is very similar to the casting one, but there could be a reduction in weight and lead time reduction. Casting initially can take up to 10 months to get an initial cast made. Where additive, this part was done in 119 hours. So 10 months versus 119 hours, this part was made significantly faster than, say, an initial pre-production prototype casting, which could take, again, up to 10 months, and elimination of that supplier and the supplier contact by bringing this operation in-house and moving the powder bed. Aftermarket automotive application. This is one of our customers that does high performance automotive applications, printing exhaust manifolds out of 625 Inconel. And then also turbocharger applications and intake manifolds for intercoolers out of aluminum. And so here's the actual performance testing. So this is a Porsche 911. This exhaust manifold is printed, and this part is being heat cycled to glowing red capacity. This vehicle produces 900 to 1400 horsepower based on turbos, specs, and this part performs. It doesn't crack. It's significantly lighter than the traditional cast piece. It flows better because it's optimized. The collectors are optimized. Everything's optimized and be able to print that way. And so reducing weight, increasing performance, and it's performance that works. It's performance that lasts. It's strong. These components work. And here's some more examples of just traditionally manufactured versus additive manufactured potential parts. We're looking at, you can see big, heavy, traditionally simple pieces that are then being reduced into very, very complex geometries that are as strong, but also significantly lighter weight. And actually the bottom right-hand corner piece, this is a really cool piece because this is a part that SLM Solutions produces for ourselves. So our gas tubing on our systems are all handled by DN40 vacuum fittings, which is what you see here. That DN40 vacuum fitting doesn't, it has very limited designs. So one of the areas that we do, it goes 4 pieces into one collector at the top. So we actually print our own 4-into-1 collectors for DN40 so that we're able to increase our design freedom of our systems, and we're printing the parts ourselves and making them for our own system. Another thing you notice here is that there's a lot of support material inside there. So that's something that needs to be handled after the fact. But since we can't physically source that part anywhere else, it's okay for us to make it because we understand that we couldn't get this part any other way. So in summary, when we're looking at pieces, and there's, again, I realize that I gave you no set design rules here, but we typically don't do that because every time I give a rule about something, somebody calls me back a couple weeks later and said, hey, I just broke that rule and you were wrong. So I don't like being told I'm wrong, so I'm not giving you guys any hard and fast rules. But these are what we're looking at when we're looking for a part to add to the additively manufactured system. Thank you, everybody. I hope you were able to take away something from this presentation, and we'll open up the floor to any questions.
Thank you, Kyle. So, yep, if attendees want to use that question panel on the right-hand side of the control screen there, you can ask Kyle some questions. Kyle, you showed some nice sample parts, automotive, some cool-looking automotive parts. Early in the presentation, you talked about the common application of tooling and fixturing components. Can you talk a little bit about the type of applications you've been seeing recently in tooling? Is it end of arm for robotics, or what fixtures, check fixtures? What kind of applications are you seeing for metal additive on the tooling side?
Yeah. So as far as some of the stuff we've seen is like die inserts, being able to print die inserts using tool steel. We've also seen specialty bits for tooling. So if there's a very, very unique tool pathway that needs to be created, you can use actually the high-speed steel that we make to create drill bits that you can use for these high applications. But then also for tooling, as far as replacement parts, there's a handful of industries that, in general, the cost of part is very expensive to get manufactured or to get replaced by the OEM. Large production tooling, let's say newspaper manufacturers being one of them. Since it is a literally dying industry, there's not a lot of people making new components. So making replacement components using metal additive for the existing, newspaper printing presses is probably a great application for being able to do, tooling where it wouldn't make sense holding spares of, hundreds of parts or thousands of parts for the very limited number of people still running, physical newspapers. So being able to go back and print those parts off catalog is, really beneficial.
Mm-hmm. Okay. Question is, what are your comments about the timeline for seeing more high volume serial production with metal AM?
I guess I've already gone on record saying this. I'd say within the next 5 years that metal additive is going to be, very commonplace through all markets, and within the next 10 years, I could say probably every vehicle sold will have some sort of metal additive production part on it. It may be small, but there'll probably be at least one. That's kind of what I've said before, and I think I'm going to stick to my guns on that
one. Okay. Is that largely in part due to this trend towards customization? Everybody wants a special plaque on the steering wheel, or
no? I think
handle design,
I think with our
gear shift.
I think with our increase in fuel economy standards and increase in safety and obviously reducing the cost on these areas, it's going to become beneficial to be able to lightweight by metal additive, but also the fact that, with increased, you can only weld metal so fast. So, given 400 watts, say 400 watts of material, you can only weld metal so fast. You reach a point of diminishing returns on performance. But, bigger machines, more lasers, more capacity is the way forward with that. And all the systems, not just SLM included, all the manufacturers are moving towards higher capacity systems, which are going to be more geared for this high production value, not just large individual parts, but also of many, many, many smaller parts, reaching those production numbers that are more in line with a mass consumed item.
Okay, good, interesting. Question is, for a company looking to get into additive, what type of help is available in terms of evaluating the parts that a company manufactures already to determine if there's a machine or a process that makes sense for additive? What kind of help is available to evaluate parts and what machines to be used? Yeah,
so as far as SLM, speaking as an SLM employee, it is probably 60% of what I do on a day-to-day basis is part evaluation. So that particular person asked that question. If you are interested in evaluating parts, get in contact with us, create a contact. We can start talking about what parts make sense, what parts don't make sense. We have cost estimations. We're more than happy to sit down and figure out what parts you may have that do or do not make sense. There are also some consulting agencies that do kind of that, but also do a lot of redesign for additive as well. So not just taking traditional parts, but also redesigning them. But, SLM, we understand what it takes to run these systems because we do it every day and how much it costs to run these systems. So we're probably the best source of being able to say this part yes, this part no.
Okay. Any more questions for Kyle? Okay. Can you explain how the SLM process is different from an FDM process?
Yeah. So the powder bed process is literally a bed of powder, and then the materials sit there by gravity, and then a laser passes over the material, welding the desired material. So when you're done, you have your welded material inside a bed of unwelded, powder. For the FDM process, the head, the extrusion head, is what's laying down your material, and it's only laying down material where you want it. So it will extrude out of a head, and that's more of a direct. So it would be a direct deposition, where powder bed lays down a wide bed and then lasers where we want the part to be built. So as the part you see here on the screen, inside the machine, that would be completely covered. That 280 millimeter square would be completely filled with powder, and that part would be buried. We'd need all that material there and then all that material just gets brushed away. It's still soft, it's still powder, so it gets brushed away and you're left with what you see here on the screen.
Gotcha. Okay.
And FDM is not welding. It's bonding together. Even in a metal FDM process, you're bonding together stuff using an adhesive and then baking it together. So there's a lot of layer lines and there's fault lines. Where it's welding. And every time we weld multiple layers deep. So we're creating much stronger grain structure and much more closely related to what real, cast to forged aluminum or cast to forged metal would be.
Right. So it's stronger. Is it more consistent throughout the part as well? Less variability in mechanical properties?
Yeah, and also you have, with FDM, especially FDM metals, you have limitations on thicknesses, actual like wall thicknesses and volume thicknesses, where with powder bed metal, and that's because there's binder inside there that needs to be baked out. So if you say you have a 3-inch cube with FDM, you're not going to be able to bake the binder out of that. But with metal powder bed, there's no binder to be baked out. So you can weld a 3-inch cube no problem, and you can weld any geometry you want no problem, because there's no post-baking process that's needed to create the solid metal afterwards.
Excellent. Okay. Any more questions for Kyle? We're just about at the end of our time here. Kyle's contact information is up on the screen if you do feel like you want to reach out later. Otherwise, thank you, Kyle, for that great presentation, and to our audience, thank you for attending. We hope you found it to be a valuable experience. And again, please remember that an archive of the recorded program will soon be available on our website. Once we do post it, you'll get an email from us so that you'll be able to review what you learned today again, and also share it with others within your organization. So again, thanks to everybody, and you may close your browsers now. Have a great afternoon.